Okay, you have probably noticed at this point in the course that there are quite a few similarities between the theories of heat transfer, mass transfer in particular, and also some similarities to the theory of momentum transport. So to sort of lay those out formally, we have Fick's law, which is labeled Fourier's law. Sorry about that in this set of notes. So we've got the mass flux is a diffusivity multiplied by a concentration gradient. And in Fourier's law, labeled Fick's law here, sorry about that, the heat flux also has a coefficient. This is this alpha parameter, thermal conductivity over a heat capacity, multiplied by a derivative of the thermal energy density. So you can think of that as being analogous to a concentration. And in Newton's law, we have a shear stress multiplied by a coefficient that is the kinematic viscosity times the derivative of the momentum density. And so these things are, transporting moles per volume, energy per volume, and momentum per volume. And it's kind of useful, I think, to, Kussler goes through and outlines this, and it's kind of useful to see the way the solutions to, say, Fick's second law, Fourier's second law, all these kinds of problems give you very, very similar solutions. For example, if you take a semi-infinite slab of, say, this is going down into a liquid from the surface, with the surface being right here, and you suddenly contact that liquid with some solute, the concentration of solute at the surface immediately jumps up to the saturation value, and the penetration depth gradually goes deeper and deeper into the liquid as time increases. So the analogous problem in the theory of heat transfer is that you take a infinite well of liquid initially at one temperature T naught, and you somehow change the temperature at its surface to this Ts, and the solutions from Fourier's law will come out to be look like a penetration depth of a thermal layer going deeper and deeper into the liquid. So we can imagine the same thing for momentum transport, where you take that liquid of infinite depth, and at the surface you place it in contact with a plate that suddenly starts moving at velocity vs. And we can think about what the velocity profile as a function of time and position down into the liquid looks like. And initially the surface of the liquid starts to move with the plate, and gradually that motion penetrates deeper and deeper into the liquid layers. So all of these things have very, very similar solutions. You can see that all that's changing here is the argument of the error function and the way we non-dimensionalize the problem. And so to make the analogy concrete, the diffusivity corresponds to this alpha parameter for heat transfer, and to the to the kinematic viscosity in the case of momentum transport. So Reynolds, recognized this and wanted to try and make these analogies useful for being able to predict things like heat transfer coefficients and mass transfer coefficients from friction coefficients. So he envisioned this separation of heat, mass, and momentum transport into contributions that come from the quiescent process, that is when the fluid is not moving, and also contributions that come from convective processes when the fluid is moving. And in his early days, Reynolds thought that all fluids moving were turbulent, and so that's the way he describes it. But of course we know that there are also laminar processes, and we can think about convective contributions to their transport as well. So what Reynolds assumed was that you could write the mass transfer coefficient, the heat transfer coefficient, and the friction factor all in similar forms. And here was the idea. You have the constant term that comes from the quiescent transport, and you have the convective term that's going to have some dependence on how fast the fluid is moving, the velocity, and some coefficient. And so this thing in square brackets here represents, in this case, a mass transfer coefficient, right? So it's giving you the total rate of mass transfer in terms of quiescent rate and a convective rate multiplied by the concentration driving force. And then we have, he also wrote down the heat transport rate in the same manner, right? So we've got a different coefficient here for the quiescent transport of heat. That would be your thermal conductivity when everything is still. Then you have this convective transport contribution, and I'm sorry, that's supposed to be a delta T here at this point in the notes. It's heat transfer, so it should be multiplied by a delta T. And so he took this a bit farther, and he said you've also got a shear stress that can be written down in terms of if you envision, this being the concentration at saturation minus, or the concentration at the interface minus some concentration out in the bulk. This would be the velocity out in the bulk minus the velocity at the interface, right, which is going to be, for no slip, is going to be 0. And so you can imagine this being analogous to the delta C here, and then the FV over 2, which is the way we know that the shear stress is related to velocity when you have one of these friction factor correlations, gives you the thing that must be analogous to what the heat transfer and mass transfer coefficients are doing. So this FV over 2 doesn't have a quiescent term, and the idea is that for there to be a shear stress, there has to be some motion of the fluid. Okay, so we drop that term and recognize that we believe that this FV over 2 then must somehow, Reynolds believes that this must somehow be analogous to the B times a function of V and B prime times a function of V, and also imposed the view that whatever that function g of v is, it should be the same for all three processes, right? So here's the idea, right? We've got convective transport should look the same for the mass transport, heat transport, and momentum transport. And we should multiply those by the difference from the wall out into the bulk, right? So in all cases, we're multiplying by delta C, delta T, and delta rho V if you want, but rho V is just going to 0 at the wall. Okay, so that's basically the idea behind this. Now, he further supposed that all of these convective terms were similar, right? So these are the convective terms, and he supposed that B is equal to B prime is equal to B prime prime, okay? And beyond that, he said, well, if we've got transport due to convection, then the transport due to these quiescent processes are going to be negligible, right? So he said we'll just assume that those are 0. And now he obtains an analogy between the mass transfer coefficient and the heat transfer coefficient and this friction coefficient, right? So you see that if you make these assumptions, then this is what comes out, right? And that all of them then are going to be equal to this unknown B times this unknown function g of v. So we don't really care about this guy. What we care about is what's on the left side of this equation, and that's an equality between the mass transfer, heat transfer, and friction coefficients. Which is, that would be pretty remarkable if it works. And the question is, does it work? Well, it turns out that the Reynolds analogy works quite well for gases. That is to say, if you're in the gas phase and you know the heat transfer coefficient, you can divide by the heat capacity and get your mass transfer coefficient. And if you know either of those things, you can estimate the friction factor in this way. So it works pretty well for gases, but it does not work at all for liquids. And so can we rationalize this? Yes. So the idea is that we can think about this mixing as taking place at two different levels in the fluid. We have a macroscopic type of mixing, which is accounting for turbulence and convective flows out in the bulk of the fluid, and we also have microscopic mixing, which is diffusion, conduction, and depends on the viscosity that you have in the boundary layer, right? So now for a gas, we're going to use the fact that the Schmidt number and the Prandtl number are both approximately 1, right? And the result of that is that the diffusivity and this alpha parameter and the kinematic viscosity are all on the order of 0.1 centimeters squared per second, right? So you can think of it in terms of this saying that these things are all about equal to 1 is the dimensionless numbers statement of this, actual quantitative statement with units. That all of these coefficients that govern mass transfer, heat transfer, and momentum transport, they're about the same for a gas. Remember that the mechanism of dissipation was the same as the mechanism that was causing the fluctuations, we argued, at the microscopic level. And so they must be the same. And so that's not the case for liquids, right? So in the liquid phase, the Schmidt number, which is related to the mass transfer rate, is on the order of 1,000, and the Prandtl number is usually on the order of something like 10. But the key thing is that the Prandtl number and the Schmidt number do not have to be the same in the liquid phase, and therefore this Reynolds analogy really doesn't work so well in the liquid phase. Remember when we did our boundary layer analysis, and we showed that the Schmidt number related the boundary layer, the concentration boundary layer thickness to the hydrodynamic boundary layer thickness. And so by the same arguments, we would have found that the Prandtl number relates the thermal boundary layer thickness to the hydrodynamic boundary layer thickness. Now, if the Prandtl number and the Schmidt number are very different, that means that the thermal boundary layer and the mass boundary layer must also be different, and that's going to give you very different rates of heat transfer and mass transfer at the same velocity profile. And so that's basically why the Reynolds analogy does not work in the liquid phase. But Chilton and Colburn came along, and they said, can we somehow just rescale things by the Schmidt number and the Prandtl number in a way that will correct for this? And so here was the Reynolds analogy, and what Chilton and Colburn did, well, first they divided through by the V, and then they got a Stanton number, K, the mass transfer coefficient over the velocity, multiplied by Schmidt to the 2/3 is equal to the heat transfer coefficient over the heat capacity and the velocity, that's a thermal Stanton number, multiplied by the Prandtl number to the 2/3, and now that is equal to the friction factor over 2. Okay, so you'll commonly hear these called Chilton-Colburn J factors for mass transfer and J factors for heat transfer in the literature. A lot of correlations are given in terms of these two J factors. They're quite useful things to know because now this Chilton-Colburn analogy really works. In fact, when you put this Schmidt number to the 2/3 and Prandtl number to the 2/3 in here, it really patches up a lot of the problems. There's some amusing anecdotes in the Kussler book about how they arrived at this 2/3 factor. According to Chilton, it was because their slide rule only computed cube roots and square roots, and so that was the convenient discretization, and the cube root to the cube root squared worked better than the square root. So they went with that, and it turns out to be quite powerful result. So I think we'll stop there and do some examples using this Chilton-Colburn analogy in the next session.